My video got cut on the last one, so hopefully you guys can watch these videos back to back. But what I was saying was that I prefer sometimes leaving your fraction as it is. I mean, if you can simplify it, of course, try to simplify. Like, for instance, here I know 10 goes into 180 and 10 goes into 50, so I would simplify it. Again, you can always convert it to a decimal, but sometimes your decimal, your calculator is rounding some of those numbers. So your probability might not be exact. So sometimes I'm okay with you just leaving your probability as a fraction. But if you want to convert it to a decimal, you can. Just be careful when you're doing it. Again, you either give the exact fraction or a decimal or round off final decimal results to 3 significant digits. So again, either leave it as a fraction, or if you convert it to a decimal, leave it to 3 decimal places, and so on. So let's look at this idea where it says the law of large numbers. What this law of large numbers is saying is that if you continue a procedure long enough, that you're actually looking at the outcomes. So, for example, flipping a coin. You're flipping the coin, you're seeing the outcome that you're getting. You're either landing heads or tails or whatever it may be, but you're actually seeing that outcome. The law of large numbers says the more you do a procedure, the more likely or the closer you're getting to the true probability. So by true probability, I mean the chances that something that an outcome is going to happen already. And you just know that's the probability of it. Again, historically, flipping a coin, we know that there's a 50% chance of landing heads, 50% chance of landing tails. But if you do what I said earlier about flipping the coin 100 times and then seeing how many times landed heads versus tails, you're not going to exactly have 50-50 because that's a procedure and we're sort of already choosing 50-50 in the classical approach. So the law of large numbers will just show us that if you do it enough times, you actually, maybe if you only flipped it 10 times, it's possible that all those 10 times landed heads. But once you flip it 100 times or 200 times, it's going to start evening out. Meaning that the number of times you land tails, you flip tails, you're going to have almost an equal amount of times that you land heads. And that's the idea of law of large numbers. Hopefully that makes a little bit of sense. Again, as a procedure is repeated again and again, the relative frequency probability. So that's when you actually create a procedure, sort of like how we collected data. And you sort of input, each outcome has its own category, the same way we did a frequency table before. Like when we did the one for like grades, each grade had its own category. Or the taste test that we did, each sort of taste and grade had its own category. And then the frequency is you saw how many times that category occurred. In this situation, the categories are the possible outcomes. And then the frequency is just the number of times that outcome occurred. And if you do that procedure enough, that the probability that you get will actually get closer to the actual probability. So again, if you want to try that with flipping a coin, you can. Flip it 10 times, calculate your probabilities there, flip it 5 times, and then you might see that majority of those times you landed heads, or maybe you do have a 50-50. But then at 10, you'll notice you have more heads than tails. Maybe at 20, you might notice that you end up getting more tails than heads, and so on and so forth. But the more times that you repeat it, the closer and closer you get to that 50-50 probability that we know to be true. But you can see that. So try doing that and see what you get. But let's look at an example. Somehow, this all got deleted here. So the example was for a relative frequency skydiving. Let's say we're trying to find the probability of dying when making a skydive. So where we're using the relative frequency approach here. So what that means is that we personally don't have to go skydiving a million times to verify how many of those times you die, because that would be kind of weird. Because if once you die, then there's no way to calculate it. But a way to do this example is you actually go look at how many people maybe have skydived in the last year, last 2 years, however time frame you have. You look up or in general, how many deaths have there been in skydives, or how many deaths in the last 3 years versus how many jumps there's been in the last 3 years. And then you can see out of all those jumps, how many of them actually died. So here was the question that gave us that we looked at 3 million different skydives. And from those 3 million different skydives, 21 of those jumps resulted in deaths. So if you're trying to find the probability of dying if you go skydiving, so probability of skydiving death. So dying if you go skydiving. So the event we're looking at is the possible deaths. How many ways did that happen? That happened 21 different times. So the number of skydive deaths is 21 over however many skydives there have been or that you were looking at. And of those 21 deaths, that came from 3 million skydives. And from those 3 million skydives, only 21 of them resulted in death. So that probability, remember, it's 0.0000. Normally, I don't want you to write up to that far. But it happens to be the probability so small, meaning it's really close to 0, meaning it's very unlikely. So if you want to go skydiving, again, I don't promote it, but it's very unlikely for someone to die through skydiving. And that's just doing the relative frequency approach. Again, the number of ways the event can happen, the probability you're looking for. In this case, the event we're looking for is possibly dying during a skydive. There's 21 deaths out of 3 million jumps, skydives, which is a very small probability of death. The issue is the reason why you want to use the relative frequency approach here is because you're actually using data. You're actually looking at what has happened and you're basing it off that. If you tried using the classical approach, that's not a really good way to choose, because the two outcomes, dying and surviving, are not equally likely. And that's something else that's sort of overviewed, but the outcomes should be equally likely to happen, because if you already know one's going to happen over the other, that's going to sort of skew your probability. For example, let's say you're flipping a coin and you're dealing with a two-head coin, meaning every time you flip that coin, it's never going to land tails. You're going to have 100% probability of landing heads. So that's unfair, because that's not, if both sides have heads, then let's say if you're playing with somebody and you call tails, you have no chance of winning, because it's not even likely, it's impossible that it's going to land tails if it's both sides are heads. So that's why it's important that you're dealing with that everything has an equal chance of happening. So when we look at the probability here, if we try using the classical approach, I guess the only two possible outcomes here is either you live or you die. And that would seem like your denominator would be 2. Those are the total possible outcomes. You either live or die. And then if you're doing it the classical approach. And then your numerator, again, you're trying to find the probability that somebody will die during skydive. If you take the classical approach route, your denominator is 2, and there's only one way you can die. In the sense of, you don't die different. Yes, you can die like drowning, burning, but once you die, you lose your life. There's only one way that can happen. You're gone. But if you did 1/2, meaning there's only one way you can die versus the total possible outcomes is either you live or you die. Those are the total possible outcomes. But then that would mean there's a 50% chance if you go skydiving that you're going to die. But we already know that that's not true. And we know that because if you had a 50% chance of dying, that means of these 3 million jumps, 1.5 million should have died when they did their skydive. But the nice thing about the relative frequency is that you get to actually see what happened. You saw 3 million. That's a lot of jumps. So you get to see all those jumps and how many of those were deaths. So it gives you an idea of what is going to happen during the skydive. Versus if you did the classical approach, you can only die one way. You either live or you die. Those are your total possible outcomes. Seems there's like a 50% chance. But that's definitely not the case, because living and dying, you don't have those two events are not equally likely to happen. Now, if we took the third approach, again, if we use the subjective probability, for the most part, again, the subjective probability comes from prior knowledge that you have. If someone asks me, what do you think the probability of someone dying while skydiving is? Again, just from my knowledge of seeing people skydive or hearing about skydiving and watching different skydives on YouTube, I would guess it's a very low chance of you dying. I probably would have guessed like 1 or 2% chance of somebody dying, which I'm not too far off. The classical approach would imply it's 50% chance of dying, which is definitely not true. So classical approach definitely won't work here. Relative works great. You just have to find all the skydives and how many died. The subjective probability can also be useful here, as long as you're using like a knowledgeable resource. Again, for a probability like this, if you told somebody what's the chances of you diving while skydiving, they might say there's a very, very, very small chance. They might say it's like less than 1% chance of it occurring. And that's just a subjective probability out of just historical data and just seeing people skydive and not hearing. And maybe in your lifetime you haven't heard a story of someone dying while skydiving. So that's you taking your historical data and then trying to make a probability based off of that. But let's do one more example here. So say in a study of U.S. high school drivers, it was found that 3,785 texts while driving during the previous 30 days. So in the last 30 days, they saw that 3,785 texts. And 4,720 did not text while driving. So that just gives you an idea of 3,785. 3,785 are texting. 4,720 are not texting. That's in the last 30 days. Okay, based on the data that we have here, based on these results, I'm sort of skipping all this right here. I'm going based off these results. If a high school driver is randomly selected, find the probability of he or she text while driving during the previous 30 days. So again, the fact that we actually have data on how many people were actually texting and how many people didn't text, well, you have to go back to the formula. the relative frequency. It's the number of times A occurred. So what's the event we're trying to find the probability for? Find the probability that he or she actually texts. So that's the probability we're looking for. We're looking for the probability that if you pick from everyone that they tested, what's the chances that person you picked was one of the ones that texts while they were driving? Again, my denominator has to be the number of times the procedure repeated. In other words, how many people did they check if they actually were texting while driving? Well, we know if they know that 373,785 texts, that means they asked those 3,785. If we know 4,720 didn't, they had to have asked them. So we need the total number of people that were surveyed or were part of this procedure. So that means we have to actually add them together. Because I already know how many texts. And that's what I'm trying to find the probability of. I'm trying to find the probability that I randomly select one person. What's the chances that they were one of the ones that were actually texting while driving? I know 3,785 did, but I don't know how many out of. So I need to see how many people were surveyed. And if you add those together, 8,550 total number of drivers in the sample. So that's the sample that they created. But from those 8,505, 3,785 were texting. So if I calculate the probability, it's how many ways it actually occurred. That means I'm trying to find the probability texting while driving. So that's how many times did that occur? That occurred 3,785 times. Out of 8,505 that actually were texting while driving. So here's my probability. So there's a 0.445 chance that if you randomly select from those 8,505 students, there's about a 0.445% chance that one of them was texting. Again, if you want to convert your decimal to a percent, we talked about this before. Just move your decimal over 2 places to the right. And instead of saying 0.445, you can say 44.5%. So there's a 44.5% chance that if you randomly pick one of the students that were surveyed, there's a 44.5% chance of selecting somebody. So, for example, so this is the interpretation. This is how you would read it. There is a 0.445 or a 44.5% probability that if a high school driver is randomly selected, he or she texts while driving during the previous 30 days. So again, there was 8,505. If I randomly pick one of those, there's about a 44% chance that one of these I picked would text while driving. There's also this idea of the complement. So the complement are all the events that don't involve a particular event that you're looking at. So, for instance, if you're looking at the complement of event A, so the way you denote the complement is everything else in the sample space, not including the actual event A that you're looking at. So, for instance, if you're looking at the event A, let's say the event of rolling a 1 on a fair die, so that's the probability, that's the event that you're looking for, rolling a fair die. The complement of that is the rest of the sample space. what I mean by the rest, that is landing 2, 3, 4, 5, and 6. That would be the complement of event A, the probability of landing all the other ones. So the complement of event A, that's the denotation. This is known as a bar. They call that A bar. So it consists of all outcomes in which A does not occur. So that example that I gave you, rolling a 1 on a fair die. So that's event A. The complement would be every other event that doesn't occur A in it, meaning landing 1 on a fair die. So for example, so in a recent year, there was 3 million skydiving jumps. 21 of them resulted in death. Find the probability of not dying when making a skydive. So what we found the probability for earlier was the probability of actually dying. So now we're going to look at the probability that you're not going to die. And then again, we'll probably use the relative frequency approach. Before we did 21 over 3 million, because that was the probability of how many actually died. Essentially what I'm looking for when I say not dying, I'm looking for the probability that you're actually going to survive when you go skydiving.